Hello again, and welcome back to our discussion of index structures in PostgreSQL, and in particular of the B+Tree index structure that is prevalent in relational database system and in PostgreSQL. Alright, as the name already gives away, it's indeed a tree-shaped index structure, okay? And it's a data structure that is maintained by the database system in addition to the actual associated heap file, the data file, the table. All right, so if we look at this picture, it's indeed divided into two parts. Let me draw a line here. So that would be the line. All right, so everything below that line is something that we've already discussed. It's just the heap file, the page organized heap file. So that blob here, that would be one of these 8 kilobyte pages that we have talked so much about already. Okay, so that's the heap file that has been there all the time. Above the line is the new structure, the tree-shaped, the B+Tree structure. It's also organized into individual pages, 8 kilobyte pages. You see there's a root page here where all the search processes in the index actually will start. And the pointers inside this tree structure will lead us to inner node pages, all of size 8 kilobytes, which will then eventually lead us to leaf pages at the leaf level of a tree, where we also find 8 kilobyte pages. So all of the nodes in that tree structure are indeed 8 kilobyte pages. That means that such a node probably has lots of space to store pointers and keys and pointers, just like a search tree structure that you know from other courses in your studies. This is a search tree structure that will have a rather high number of pointers, of child pointers, pointing from these inner nodes to the lower subordinate levels, to other inner nodes, or eventually to leaf pages. Okay. These leaf pages are connected to each other in the form of a chain, or the so-called sequence set. Okay, so once my search reaches the leaf level of the tree, I can use these sequence set pointers to quickly navigate to the left and right inside this chain of leaf pages, and this will turn out to be very useful when we try to evaluate particular types of queries. Okay, inside the leaf pages, and we will have a closer look at leaf pages in just a minute, inside the leaf pages you will find pointers into the heap file, into the data file. All right, so I'm talking about one of these pointers here. All right, from that 8 kilobyte leaf page of the B+Tree, I will find a pointer pointing directly into one page of the heap file. And this pointer is actually not pointing to a page, it's actually a RID. It's actually pointing to one particular row inside the heap file. Okay, so from that leaf page inside the B-tree, I will find a RID pointer, find a RID information that directly leads me to the matching to the target row inside the heap file below here. So these RID pointers, they provide the connection between the separate index heap file, also page organized, and the data or table heap file, of course also page organized and held persistently on our file system storage. That would be the general setup of things. Okay, a few more notes about the anatomy of B+Trees. Okay, so as you can see, such an B+Tree index, and we will call them I from now on a table T. And it's also important to note the column over which we've erected the index structure. So T may have many columns, but this index I is an index particularly designed to support accesses to column A. All right, so such a B+Tree is indeed an ordered tree. All right, so we will see that order inside the tree plays a very important role. The entries inside the 8 kilobyte index pages are very well ordered. Okay, it's an n-ary tree, and that relates to my statement or my comment about the many pointers that you will find inside an index page, an inner index page that points to many subordinate pages in the tree. So this is not a binary search tree, it's an n-ary search tree, and we indeed hope that the n is much larger than 2, and we will see why in a few minutes. It's also a balanced tree. It's a balanced tree, so if we look back here, the length of the path from the root to any leaf is of the same height, the same length, all right? So all of the leaves are at the same depth, you could say, inside such a tree. This is a dynamic tree structure that may change its shape over time, or in particular, when the heap file is growing or shrinking, we will grow or shrink this tree structure, but it will always remain a balanced tree. The length of the path from the root to any leaves will be equal for all the leaves. Okay, so that would be a balanced tree. It's also a block-oriented tree. Okay, so the nodes are indeed organized in these 8 kilobyte block pages, and it's dynamic. It can react to updates. Okay, so actually this tree has been invented quite some time ago. Indeed, it has been invented by Rudy Beyer and Ed McCreight in 1969 already, while both were working at Boeing Labs. So that makes for a lot of B's there. There's a B in Boeing, and there's a B in Beyer, and there's a B in balanced, and there's a B in block-oriented, and so on. But none of these B's led to the B in the B+Tree name. Okay, so that's one of the big mysteries of computer science. Why does the B+Tree is called the B+Tree? All right, so actually, I've been working with Rudy Beyer at TU Munich for a while, and we have tried to twist his arm and lure him into revealing that secret, but Rudolf Beyer just wouldn't say. We don't know what the B in B+Tree stands for, and I don't know whether it will ever be revealed. All right, so if somebody told you, oh, this is a balanced tree, or it's the block tree, that's the B in B+Tree, no way. Rudolf Beyer just wouldn't say. Well, anyway. Okay, so it's a block-oriented tree, so the inner nodes and the leaves, they are all formed by these 8 kilobyte index pages. Indeed, this 8 kilobyte is the default size of pages in PostgreSQL. If we grow that size, the size of the node pages inside our B+Tree will grow as well. Okay. It's a search tree, all right? So in the inner nodes, we will find n-n values of column A. Column A is the index column, the column that we use to organize the B+Tree. All right. Okay. So if this is an n-ary B+Tree, then inner nodes will hold n-1 values of the A column, the so-called separators that we will be using to decide, hey, into which of the subtrees, into which of the n subtrees of this inner node shall my search for the target row descend next. Okay. So we will, of course, have a closer look at these separators, but this is just an n-ary search tree structure, and to guide that search inside the inner nodes, we will find n-1 values that separate these n pointers, and that make it clear which of the pointers have to be dereferenced and followed to guide our search. Okay. At the leaf level, we will find this bidirectional chain of leaf pages, the sequence set. All right, and we will see that this becomes very, very handy when it comes to the update, when it comes to updates on the tree, to keep its balance, but also to evaluate particular types of queries on these B+Trees, the so-called range queries, which the B+Tree is an expert in supporting. For example, hash indexes are not as well supporting such range queries. Actually, they're not supporting them at all. All right, so this is the point where we will depend on these bidirectional pointers. Okay. And let me emphasize that the pointers in the leaves, the pointers in the leaf nodes of the index point to individual rows inside the heap file. Okay, so we use a rids, we use individual rids inside the leaf nodes of our B+Tree to point to individual rows that we want to target in our search. Okay. Besides Besides the A values, the separator values that guide our search in the inner index nodes, and besides the A column values that are associated with the RIDs here inside the leaf pages, as you will see, there is no other data, no other row data from column T is to be found inside such a B+Tree index, unless we explicitly put it there. Okay, so in a vanilla B+Tree, all we find is the key values, the A values, the separator values that help us guide the search, and nothing else of the base data of table T is being found in the index. This, of course, helps to keep the index lean and help keep it small. Okay, so I think it's time to have a closer look at one of these leaf nodes. So let's focus on the leaf nodes first. There's already interesting stuff to be found there and to be said there. We will have a separate video on the inner nodes of the B+Tree in a short while. But for now, let's look at the leaf nodes. And what you can see here in this schematic drawing, let me circle that. This guy is one leaf node, and it thus occupies 8 kilobytes of space. Okay, so this would be a zoom into the 8 kilobytes of space inside one leaf node. Okay, as you can see, we will find these bidirectional pointers that help us to form the sequence set, the bidirectional chain of leaf nodes. Okay, so a next pointer will point to the next leaf in the chain, and it's bidirectional, so a previous pointer will point to the previous pointer in the chain. Maybe there is no previous pointer in the chain, so some nodes will of course be the first or the last pointer inside such a sequence set. Okay, so we'll then find index entries inside these leaf pages, and this is one index entry. It's a pair. It's a pair of a key value of an A value in this particular case. If this is an index over column A, this K here, this K3 will be one A value, one element of the A column inside table T. It's associated with a pointer, with a RID pointer, as I told you already. This pointer would point into the data file of table T. And it's of course our expectation that when we follow this RID pointer into the data file, if we follow pointer RID3 that is associated with K3, then of course our expectation is that the row that we find in the data file will have an A value that equals K3. Okay, so the semantics of, let's look at this guy. The semantics of this index entry is follow my RID. If you do that, you will find a row in the heap file, in the data file of the table, and its A value will be K2. That's the semantic of such an index entry here. All right. I was talking about the ordering of these of the tree, and indeed, this is an ordered sequence of entries inside one leaf. So the K, the K here, the A values, they are indeed ordered, and there is a guarantee that K1 is no larger than K2 and K2 is no larger than K3. This is the ordering I'm referring to here. Okay, so if I walk this leaf from left to right, I will see ascending K values. All right. This will help me search this list of entries, of course, once my search from the root of the tree leads me here. To complete the search, I can use the fact that the K values here are indeed ordered. I can use binary search among these leaf entries here, among these K values, to quickly locate the entry I'm looking for, if it's there at all. Okay. There's one additional piece of information inside these leaf nodes. It's the so-called high key, okay? And the high key, you see it referring to this KL+1, which is repeated over here. Okay, over here. So this is information that I can already access when I only have loaded this 8 kilobyte page. This is information about what I will find if I walk the chain, the sequence set chain, further to the right. So if you walk the sequence chain further to the right, the smallest key value that we will find in the next page is k l plus 1, and this is repeated and copied here. Sometimes that's very useful information that maybe keeps me from following this next pointer into the next 8 kilobyte page that I have to load, of course. Sometimes this might keep me from following that next pointer at all, because I can see that there I will find values kl plus 1 and larger, of course, that are not relevant to my current search. Okay. So I think that's the anatomy of a leaf page. I think it's time to switch over to the terminal again and see if we can find all these bits and pieces in the real PostgreSQL system. So let's do that. Let's switch over. Because it's now time to look inside individual pages again, in this case it's to inspect the innards of a leaf node page, index leaf node page. We will activate our page inspect extension again. This is the well-known extension that we've already used to inspect the internals of a normal heap page inside a table. We can also use it to inside the index pages, leaf nodes and also inner nodes. Let's do that. Let's activate the extension. Already exists in my database, of course. All right. Okay, so now let's remind ourselves about the heap files that are associated with our table and the index, and let's see in particular how many pages are there inside our index structure. Okay, so we've seen that before, but if you recall, 2,745 pages are in the heap file that represents our B+Tree. So this is really an n-ary search tree structure maintained on disk in 8 kilobyte pages in 2,745 8 kilobyte pages. That's quite the index structure. Okay. So let's see some of the details of these pages, of these B+Tree pages. To do that, my next queries will dump some of the internals of these pages, and because there is a lot of internals to look at, I will switch on the vertical display of rows in my PostgreSQL shell. You will see how that looks in a minute. It makes the inspection of very wide query results a bit easier if your terminal or your editor is narrow. Okay. So that's what I'm doing here. I'm using a generator that will generate values p ranging from 1 to 2044, 2744. I'm sorry about that. So that's almost all of the index pages. Almost all of the index pages you see, there is 2,745 pages in all, but there is one page among them, the page 0, which is very special. Let's not look at this particular special page now. We will come back to that. Let's look at all other pages, okay? All other pages P. And here I'm using the page inspect extension to look at one particular page of the indexed _a index, the B+Tree that is in question right now. I will look at page P, but only if this particular page P, that node, pages and nodes and a B+Tree are synonyms, only if this particular node in the B+Tree is indeed a leaf node. You see that its type indicator is L for leaf here. If this is the case, I'm interested in seeing that. Actually, I would see 2,744 entries now. Let's limit that to the first three. To the first three here, that's already sufficient to see what's going on. Okay, so let's do that. Okay, so here you can see the vertical display of rows. I think that's more appropriate here to inspect what's going on. So what you can see here is data about the block, the page number 1 inside the heap file for our B+Tree index, and it's indeed a leaf node page. All right. Okay. we can see that it has previous and next pointers that connect it to the other pages in the sequence set in the chain of leaf pages. So let's see, this 0 indicates that there is indeed no previous page in sequence set. We are looking at the very first, at the leftmost page inside the sequence set. But there is a page to the right, a next page. It's page 2, and it's indeed that page that we've listed below here. Okay, so page 2 then points to 4, which is the next page that we've outputted here. Perfect. And that would point to page 5. We have not further printed here, but it would also refer back to 2, which is this page, which will refer back to 1, which is our first page again. So indeed a bidirectional chain of pages inside the sequence set. Inside that sequence set, we find 367 index entries. Okay. Actually, it's indeed only 366 entries. Let me tell you that it's only 366. One of these entries is used to represent that high key, the lowest key on the following page that I've already mentioned. So it's actually only 366 entries here plus 1 entry reserved for the high key. All of these pages have a high key entry unless I am the rightmost page in the sequence set, then there would be no high key entry, of course. All of these index entries, these key read pairs, occupy 16 bytes. All right, so we know that a read in PostgreSQL occupies some space. The rest of the space is occupied by the key value, the A value, obviously, that we've stored here. All right. The page indeed has a size of 8 kilobytes. Well, we knew that already, and there's some free space actually on there. 808 bytes are currently unused on that leaf page, so there would be space still for more index entries that we could save there. Okay, why these are indeed these 800 free bytes are found actually on almost all of the pages. So almost all of the pages leave some free space here, is a topic that we will address in a short while. There's other stuff to be found here in these entries. For example, this BTPO, this 0 value, indicates that these nodes that we are currently looking at are located at level 0. Counted from the bottom of the tree, they are at level 0 of the tree. So the inner nodes just above these leaf nodes would be at level 1. Above that would be level 2. At the highest level, we would find the root node of this particular B+Tree. I think that's all I wanted to point out in this output. Okay, so let's see if there is indeed 8 kilobytes of space and only 366 entries have been occupied, and all of these entries have a width of 16 bytes. That means that I'm sorry about that. Okay, that means that 5,856 bytes only are currently being used for index entries in this leaf page. And that's, well, that's only 71 or about 70% of space is only used inside the leaf pages. The other 30% appear to be unused or free. And as I told you already, this is for a good reason. We will come to that when it comes to the updates on this B+ structure or B+Tree structure. Okay. Let's switch back to the normal horizontal display of rows. All right. So what you see here now is a more complex SQL query. If you cannot grasp the details of this particular query at a first glance, I would consider this normal. All right, it's a recursive query. It's a recursive query that I'm using to walk the sequence set, this chain sequence of leaf pages. All right, and I'm doing that to just count the numbers, of index entries that I can find if I walk the entire sequence set from the beginning to the end. Okay, of course, I would hope that I find 1 million index entries, because there is 1 million rows to be organized in my indexed table. All of the rows, all of the 1 million rows should be represented by one index entry in the leaf pages of my B+Tree. So let's see whether this indeed can be found. I would start my walk at the very left end of the sequence set chain, and this is the query that would indeed find that very leftmost page. So let's see if this is indeed doing the thing what we expect. We would start at the system catalog that tells us about all the files inside our system and even more stuff. But we would only look at the file that is associated with the indexed A, and to make sure that we are really looking at an index file, we would also look for this rel kind equals I here. Okay, so this is indeed, C is indeed the heap file that represents our B+Tree index. We would then check how many pages we can find in that index. All right. -1, because there's a special page 0 that I would just not access at this particular point. All right. So for all of these pages P that I've identified that far, I would then indeed look at the internals of that page. Look at the internals of that page P inside my B+Tree index. And I would call that particular page, or the node of the B+Tree that I'm currently looking at, I would call that node. Okay, I would make sure that I'm only looking at leaf node. There would also be inner nodes inside the tree. Among these c.rel pages, there will be many inner nodes. But I only want to look at the leaf nodes. I want to walk the leaf node sequence set chain, and I would to start at the very left. The leftmost node in this sequence set chain has no previous entry, and that's indicated by this 0 here. Okay, so this would actually locate the leftmost page in the sequence set of my indexed A B+Tree. Okay, and once I found that, I would simply print or simply output its block number. Which page inside the file are you? Where would be the next page in the sequence set? This is very crucial because we want to walk the chain. All right, and then I would just print or would just output the number of items, the number of index entries that I've found on this particular page. I would subtract 1. I would subtract 1 if there is no next. Well, I would always subtract 1 for the high key unless I'm at the last page in the chain, when there's no high key, and nothing would have to be subtracted here. Okay, so that's really tricky logic there. Okay, so this would be the first page in the sequence set, and this union all part below would identify all the other pages step by step. So each iteration of this part of the query will identify the next page in the sequence set chain. We will do that until we find a page that has no next entry. Okay, so well, we would start from the sequence set that we have explored so far. From that, we would look at the s.next at the next page, and for the next page, we would find the B-tree internals, the B-tree page internal data. We would call that node and do the same thing that we did for the first page. For all of these pages, we would just record the number of live items, and of course account for the occurrence of a high key if it's there. So that's this recursive query. It's one of the more complicated queries that you will see in DB2. If you are in the advanced SQL course, you will learn to read and also write such queries, which are super powerful. Recursion opens up a whole new world of SQL querying, but that's something for a different day. Okay, so once I've walked the entire sequence set, that's fine. I will then just sum up all the entries that I've found, and I hope that all the entries, all the index entries that I've found on all these pages, that they sum up to 1 million. Okay. Whoa. All right, 1 million indeed. So no row has been forgotten. All of them are being represented in the sequence set of our B+Tree index. So this has been a walk across the entire chain of leaf pages. Let's now focus on one particular page, or leaf node page inside this B+Tree. Okay, and let's focus on the page with number 1, the page or block number 1. And as you recall, let me scroll back here. Yes, this page number 1. We found that already when we were looking at a sample of leaf pages. This is indeed a leaf page of my index. So let's see what we can find there. Okay, we can find 367 entries. Okay, I think that's to be expected. So this is really a look at the different index entries inside this leaf node page. Let's scroll to the beginning here of the display. Okay, there we are. Okay, so item offset, this is just the number of the index entry that we are looking at inside our leaf node page. And as you know, the very leftmost entry is the high key that actually points to the entry with the smallest A value in the next page in the sequence set chain. This is this particular guy. Okay, so actually it points to, this is the pointer actually, this 3 here. It points to page 3, which is the next page in the sequence set. You can check that if you scroll back up here and check that indeed page 3 is the next page in the sequence set. Okay, so this would be the high key. Okay, so let's look at this. Let's not further look at this. Let's look at this entry. This is the first real index entry. It's a pair, as I told you. It's a pair that consists of a key value, This is the key value stored in 8 bytes here, and a pointer, a read pointer that points to the data file to a row whose A value is equal to this key value. Okay, and indeed here is the read pointer. We know how read pointers look like. They are a pair of a page number and a slot number on that page. So on page 0 of the data file, in slot number 1, we will find a row of table indexed whose key value is this. Okay, so this is a jumbled mess of hexadecimal digits. You should look at this from right to left. Actually, it's in little endian, stored in little endian here and encoded in hexadecimal. Well, our key values, the A values, have been normal integers, but it's easy enough to convert these hexadecimal representations into a readable integer representation. We will do that in a minute. Okay. All right. As you can see, the key values here, the key values are indeed ascending. This is indeed the key value 1. So let's convert it now. Let's convert that now. So let's convert this value. Red in little endian to an integer value. All right. In SQL, you could do it like this. So indicate this is an hexadecimal value in little endian. This would be just, or let's convert this to integer, of course. Otherwise, all right, select. And of course, that's just the one. But this works for all of the key entries here. So let's look at this entry, for example. This is at the end of the leaf node page. One of the higher keys probably on the 016D. 016D. 016D is indeed the key value of 365. Okay, so let's keep that in mind. So these hexadecimal digits, they indeed represent the A values, the key values that are associated with the index entries. So let's scroll back to the beginning here. Okay, almost there. Scrolling, there we are. All right, so indeed, as you see, the key values are ascending, and that's what we expected. This is an ordered index structure. Even the index entries inside this leaf nodes, they are ascending. And this is continuing, when I scroll through the leaf from left to right, you can see that all of the rows that are currently being pointed at are still found on the same page 0 inside my heap file. But at one point, starting with key value 6c, all right, this is changing, and we find the next entries. The next rows of our index table on page 1, starting at slot 1 in this particular case. Okay, these falses, they contain information about the fact whether there is null values that there is a null value in this key value here, or whether the pointed to row is of variable width or not. Okay, but this is not of importance here. Let's look at this guy again. This is one of the later entries. The entry at item offset 366, okay, with key value A equals 365. We have converted that just a minute ago. It's to be found on page 3 in item slot 44 of our index table. Okay, and yeah, we should actually try that. We should actually confirm that. We should confirm that this is indeed the case. When we follow the RIT from the leaf of the B+Tree into the data file, will we indeed find the expected row there? Okay, and this would be the query that we could use. Of course, that query would now access the data file itself, the table itself, and we would look at the row in whose CT ID is indeed 344. So what we expect there is a row with A, B, C column values, and the A value should be 365. All right, this is the row that is being pointed at by this particular entry in the index, and indeed it has an A value of 365, and of course some other stuff here that could be interesting for the evaluation of our query. All right, so much for a first glance at the innards of a B+Tree and the internals of leaf node pages. Okay, it's of course also important to look at the internals of the inner nodes, and there is one particular inner node, the root node of such a B+Tree, but let's do that in the upcoming video. I hope to see you there. Bye bye.